Hey everybody, this is going to be a little review session for the final test on chemistry. I'm going to be reviewing based off of the study guide that you collected in class last week and using some of the interview questions that show up at a couple different points. Let me get out of here, sorry. And so here we go. First question has to do with the atoms, and so you want to make sure that you can go and figure out where and what these particles are. So on the outside of the, that's a little funny. On the outside of the atom right here, you're going to notice that we have our electrons, and they have a negative charge. And in the center of the nucleus, we have the positive protons right here. So that's going to be our protons, and which by default leaves this other particle here in the nucleus to be the neutron. So, some of you may remember a conversation we had in class, ape, and then man in this case. You'll notice that all these letters, the A, P, E, they're all going to be the same. And so in this case here, we know that there's 3 protons. So there's going to be 3 electrons, and the atomic number is going to be 3. And then when it comes to the MAN down at the bottom here, if I know the atomic mass, in this case here I know it happens to be 7, and the atomic number happens to be 3, again that's based upon the number of protons, I can calculate the number of neutrons. 7 minus 3 gets me 4, and how many do I see? I see a 1, 2, 3, and a 4. So we'll apply this knowledge of the numbers of the particles in the atom again in a second. But for the most part, we are looking at an atom. We are identifying the particles. We are identifying their charges and the regions to which they exist. Some refer to this area on the outside of the nucleus as the electron cloud. Some people call it orbits. Depends on which model we're looking at. And then at the same time, this area here in the center is referred to as the nucleus. All right. Next up. When talking about the periodic table of elements, it should be noted a couple things are going to happen here when we look at this. First off, we're going to notice that this periodic table, all the elements are arranged by the number of protons and their atomic mass. So the lightest will be over here and the heaviest will be down here. So this will be the heaviest right here. Now, other thing to note here, as you move across the periodic table in this direction, the elements become more stable, and the most stable being this group right here called the noble gases, the NGs, and this group over here is highly reactive. The alkali metals sometimes referred to over here. Very, very reactive. That's due to the fact that they've got a valence electron of 1, or they've got 1 electron in their outer orbit, which means they're quite reactive and they like to explode at times when you present them with water. So anyhow, we'll go and zoom in on one of these here. And again, just like we were talking about before, let's see here, apologize. Hello, Mr. Adam. Goodbye. And let's see here. There we go. Nice. And now we can go and use this word bank too. Alright, so we're going to focus on helium, and we're going to identify the different parts here. So the atomic mass is right here. The symbol is the abbreviation of the elemental name. Obviously its name right here. And the atomic number right over here. So, again, if we're talking about how do we go about remembering these things here? A, P, E. Remember, these are all going to be the same. We mentioned that in the last slide. They're all going to be the same. And so the atomic number, the proton number, and the electron number are all going to be the same. And so if we're talking about helium, it has an atomic number of 2, which means it has 2 protons and 2 electrons. Now this is pretty solid and probably sometimes more obvious than not. Protons are positive, electrons are negative, and when you have the 2 of these equal to each other, it kind of helps balance things out. The other item of business here that we can apply is this MAN. Now, mass. Well, that's going to be our 4, because we can see the mass right over here. The atomic number is 2, so 4 minus 2, what's that going to be? That's a number of neutrons, we have 2. And so in this case here, this, sorry about that. So as you can tell here, we now can calculate the number of neutrons. So again, please remember that the atomic mass is based upon the number of protons plus the number of neutrons. All right, very good. Let's head on to the next question. Next question here has to do with molecules versus compounds. I think we can get to that real quick. Molecules versus compounds. You know what I need to do? Zoom out a little bit. All right, perfect. Too far, too far. Everything runs a little bit slower sometimes on this computer here. And so when it comes to bonding, why some of these elements bond together with others, and so on and so forth, a lot of it does boil down to a couple of things here. But more importantly, equilibrium and balance is the harmony of this world. And so if I'm looking at these 2 compounds that you see up here, we have 2 of them. This is sodium chloride right here. Here's your Na, there's your sodium, and the Cl for chloride. This, because it's 2 separate different elements, we're going to call this first a compound. But more importantly, it's a compound because it has 2 different elements in it. But if we were to focus on this electron right here, this electron used to be in this orbit over on the sodium side here. So this is the first orbit, the second orbit, the third orbital cloud. Now, chlorine over here has a full inner orbit, check, because you can fit 2 there. The next level, you can fit 8, and that's filled, check. And in this third orbit here, you can fit either 8 or 18. Now, if I do my counting quickly and I look around here, I notice that there's actually 7 electrons. So that means it's 1 away from being filled, or in this case here, happy and stable. Now, sodium, over here, the first 2, because we can fit 2 in the first one, check. The next orbital cloud, we can fit 8, and we've got 8, so that's another check. But this third orbit's just got 1 electron. What a pain. Because now, to become happy, I either need to get rid of 1, or I need to go and gain 7 more. And that's not an easy thing to do. And so, in this case here, these 2 elements will share, or not share, sorry, the electron will be more or less brought over, pulled over, a stronger attraction given to it by the chlorine. And so this electron kind of fills the outer orbit for chlorine, and because it's no longer causing this to be reactive, we have a nice happy balance going on here. This is referred to as an ionic bond, okay? And because this gained an extra electron, this becomes negative, as you can see right here. And because this lost an electron, it became positive. But we don't want to get too hung up on that. But just know that when there's a pulling or taking of electrons, that's ionic. Now, if we look at methane here, CH4, and we focus on these electrons right here, the dot might be from the carbon, and the X might be from the hydrogen, at which point we see that they're both sharing them because they're so close. We refer to this as a covalent bond. All right, so you have ionic on the left and covalent on the right where they're sharing. All right, let's scroll down here to the next topic, which is the difference between molecules and compounds. And when you're checking this out, please kind of observe that we've got a Venn diagram on the far left here that shows molecules on the outside. And so everything within this circle, this oval, is a molecule, but only items on the inside of this oval are considered compounds. So, compound must have 2 different elements. And we see that. CH4, CaCl. These are all compounds. HCl, 2 different sets of elements. Molecules, however, can be the just a single element like O2. So if I say molecule, this can be things like O2 or H2O, but only H2O is a compound. Again, because it's got to have two different elements. Just remember that a molecule is the smallest unit of a combined set of atoms. And in this case here, we have oxygen, we have water, but each individual one of these is referred to as a molecule. So, molecules versus compounds. Scrolling on here, let's see what else we have here. Mixtures versus solutions. I think the best way to focus on mixtures and solutions would be the idea that a mixture can be separated. So a mixture can be separated, and a solution is very difficult to separate. In this case here, a lot of times when something is dissolved, it's hard to separate. Now there are ways you could separate things, like salt water you could separate by boiling, but in terms of literally like taking tweezers and pulling things apart, that's going to be mixtures. So mixtures can be separated by physical means, and solutions cannot. Well, that didn't work. Alright, by physical means. Good, let's get out of here. Alright, scrolling down here to another question area. We have a case where we have some characteristic properties. And characteristic properties are properties that we can use to identify certain elements. In this case here, we know the boiling point of water. And so boiling point of water right down here. We know the melting or freezing point of water. That one's going to be right here. And we know the density of water. That's going to be 1 gram per milliliter. As a side note, these numbers never change. They're used as a form of identification so that we can go and figure out what these compounds, which these elements are. Alright, so characteristic properties do not change. In the next set of pictures, alright, we got to go and make sure that we understand the difference between physical and chemical changes. Now, in a physical situation, we're changing its form. We are not creating a new element or a new compound, we're just changing its form. And in chemical, we are creating something new. And a nice way to remember it is that when you go through a chemical change, it's very hard to go backwards. So if I've got a raw egg and then it becomes fried, so the raw becomes fried, that's going to be a chemical change. If I've got a piece of wood, I'm just making it smaller, it's still wood, it's just in a different form, that's going to be a physical change. If I've got water here and it's melting and then I refreeze it again and it melts and I refreeze it again, it's still water, so that's going to be a physical change. And last but not least, wood. If I was to burn the wood, releasing the carbon and the energy from the sun, that's going to be ash. I cannot get the wood back. That is a chemical change. Alright, next up. So in this one, this is all about kinetic energy and states of matter. And it goes without saying that a lot of this is partly memorization, but also partly an awareness of how the particles are moving at various states of matter. And please remember, the word kinetic energy, K-E, the kinetic part comes from kinema, which I think, kinema, is Latin for movement. Which is kind of funny because a cinema is a motion picture. Go figure. So, if I'm looking at solids to liquids to gases to plasma, and I see this over here, this total state of energy, if the energy is increasing as I move from each one of these states, the particles are also going to change and behave a little bit differently. If I'm to number these from lowest to highest, starting with the Bose-Einstein as a number 1 that's very, very cold, then go to a solid, then go to a liquid, then to a gas, and then finally to plasma at the high end of the kinetic energy, I can apply this idea. And to reinforce this by looking at some different states of matter, I've got some pictures here that we can use. And these pictures are at a level showing the molecular movement of the particles within the states of matter. And there we go. And so if we're looking at these,